Jumbo! Today we will finish our discussion of triple integrals by discussing how to do triple integrals in cylindrical and spherical coordinates. This is very much like when we discussed double integrals and talked about how to do those in polar coordinates. However, whereas most of you were probably already familiar with polar coordinates, I'm guessing cylindrical and spherical coordinates will be new to you. These are two alternate systems of coordinates in R3. The cylindrical coordinate system is very simple and is built on the back of polar coordinates. The spherical coordinate system is not too bad either, though that one takes a little more getting used to. Anyway, let's get started. We'll begin with the simpler of the two coordinate systems, the cylindrical coordinate system. Now this is a way of laying down coordinates in R3, so I'll first need to describe what these coordinates actually tell us, and then of course how to translate back and forth between cylindrical coordinates and the familiar x, y, and z of the rectangular coordinate system. So suppose we have a point in R3. We know how to find its rectangular coordinates. Starting from the origin, we go a certain distance parallel to the x-axis, a certain distance parallel to the y-axis, and a certain distance parallel to the z-axis, and those three numbers give us our three rectangular coordinates for that point. The cylindrical coordinates of the point will be a different set of three numbers. The first two coordinates of a given point will look very familiar. We just temporarily forget about the z-axis and imagine projecting the point down onto the xy plane, or up onto the xy plane if we were below it. Now that projection on the xy plane has polar coordinates, namely the first coordinate r, which is the distance from the origin to that projected point, and of course theta, which is defined in the usual way, just as in polar coordinates. It's the angle we have to rotate the positive x-axis through to get to this line. Well, those polar coordinates of that projected point are the first two cylindrical coordinates of the point we are actually interested in. And all the third coordinate does is give us the distance that our point lies above or below the xy plane. That distance, not too surprisingly, we'll call z, so that is our third cylindrical coordinate. Pretty straightforward. Cylindrical coordinates are therefore just polar coordinates with a third coordinate that gives us height. The only thing you have to remember is that the polar coordinates refer to the projection of the point down or perhaps up onto the xy plane, so that r, the first coordinate, is the distance in the xy plane from the origin to the projection of the point. It does not refer to the distance between the origin and the point itself. That's something different. So if I were to tell you that this point's cylindrical coordinates were, let's just say, 5, pi over 3, 4, that would be telling you that this distance right here is 5 from the origin to the projection of the point onto the xy plane. This angle would be pi over 3, 60 degrees, hence our pi over 3 here. And this 4 just tells me that the point is 4 units above the xy plane. Of course, not only can we use cylindrical coordinates to describe points, we can use them to describe figures in R3 as well, by writing down an equation whose solutions in cylindrical coordinates describe the particular figure we're interested in. For example, suppose we're working in R3, and we have the cylindrical equation r equals 1. What would the graph of that equation look like? Well, that would be the set of all points whose first cylindrical coordinate is 1. It does not matter what the second or third cylindrical coordinates are. Pause this for a moment and see if you can figure out what the graph would look like. Okay, did you figure it out? Let's see. Here's the graph. It's a cylinder. Every point on this cylinder has a set of cylindrical coordinates, and the first cylindrical coordinate of every point on that cylinder is 1, because if we project it down onto the xy plane, it lies on the unit circle. And more generally, if we looked at the graph of r equals c for any constant, the graph would be another cylinder. The only difference is that its radius would now be c instead of 1. So cylinders are particularly easy to describe with cylindrical coordinates, which would of course explain the name. Regions that look like this very tall wedge of cheese, are also easily described with cylindrical coordinates. This one, for example, seems to be the set of all points where the first coordinate, the r coordinate, is bound between two particular values, 0 and whatever. The theta coordinate is bound between two particular values, whatever this one is. Maybe let's just say that's pi over 3, and this one, which is pi over 2. And the height, the third coordinate, z, is bound between two particular values. Down here where z is 0, and up here where z is some other value. Maybe it's 5 or something like that. So cylindrical coordinates would describe that region very easily. Same story if we were to remove some of that, if we were to slice out some of the cheese, turning it into something like this. That z range hasn't changed from 0 to 5. The theta range hasn't changed either, from pi over 3 to pi over 2, but now the r range has changed. Instead of going from 0 out to whatever this was, we're going between this value of r and this value of r, but it's still just very simple inequalities. We might have something like r runs between 3 and 5, and theta runs between pi over 3 and pi over 2, and z runs between 0 and 5. And if we wanted to do a triple integral over such a region, these inequalities would just give us our boundaries of integration with no trouble at all. That's much nicer than if you tried to describe something like that with rectangular coordinates. You could do it, it would just be more unpleasant. So believe it or not, these alternate coordinate systems were invented to make our lives easier, at least under certain circumstances. Well, now that you know what cylindrical coordinates are, we'd better talk about the translation equations. But truth be told, we don't have to talk for very long. Since we already know how to translate between rectangular coordinates and polar coordinates in R2, and since the third coordinate in cylindrical coordinates, z, is exactly the same thing as it is in rectangular coordinates, they both just give the distance above the xy plane, there's nothing new to build on from what you learned with polar coordinates. To remind you of how this works, let me go ahead and put x and y on this picture as well. Okay, now we have our point, we have its cylindrical coordinates, r, theta, and z, and we have its rectangular coordinates, x, y, and z. How are they related? Well, by basic trigonometry on that right triangle, we have x is r cosine theta, and y is r sine theta. And those are the exact same equations we had when we were going back and forth between Cartesian and polar coordinates. What about z? How do I go from cylindrical coordinates to rectangular coordinates? How do I translate my cylindrical coordinates into the third component? Well, there's nothing to do. Z is z. It's the same in both systems. And if we go the opposite direction, from Cartesian to cylindrical, once again, the same basic relationships hold. The Pythagorean theorem on that triangle tells us that r squared is x squared plus y squared. Moreover, the tangent of theta is y over x, thanks to SOHCAHTOA. And as for z, well, that's z. Nothing needs to be changed there. So that's it. Literally the same translation equations. So if you know how to go back and forth between polar and rectangular coordinates, you already know how to go back and forth between cylindrical and rectangular coordinates in R3. The relationship that's going to be especially important to us, however, is the one that's going to tell us the element of volume, the formula for dV, an infinitesimal bit of volume in cylindrical coordinates. This too will be very simple and very familiar. Let's think about how to generate such a thing. We start at an arbitrary point in R3, and we're going to imagine sweeping out an infinitesimal bit of volume by letting this point move an infinitesimal bit in all three directions. In other words, we're going to increase each of its three cylindrical coordinates by an infinitesimal amount. That's going to sweep out a tiny little figure, which will be a rectangular box, since it is infinitesimal, and the volume of that infinitesimal box will be our dV. So let's see how that works. From our point, I've increased r by an infinitesimal amount. We can see that either directly here, or by thinking of its projection straight down onto the plane. And I've increased theta by an infinitesimal amount, d theta as well. Now before I go any further, remember what we learned in the video about polar coordinates. This length right there, or here, it's going to be the same thing down there. What's that length going to be? Well, by that basic formula for arc length of a little chunk of a circle, that is going to be the product of the radius and the angle in there, which is d theta. That means that that length right there is going to be r times d theta. And that length is the same as this length, so I will write that in right there. That length is going to be r d theta. All right, so nothing new here so far. I've increased the r value by an infinitesimal amount, and I've increased the theta value by an infinitesimal amount. But that's only given me this two-dimensional figure. To get an infinitesimal bit of volume, I'm going to have to increase the z value an infinitesimal amount as well. Doing so gives me this amount right there, which is going to be dz. So those three little increments give me these three adjacent edges on that little box. The length of this one is dr, the length of this one, back where I can't see it, is rd theta, and this one sticking straight up is dz. Now, since this box is infinitesimal, we don't have to worry about the curves there, and we can think of this as just being an ordinary rectangular box. And its volume, dv, is the product of its three dimensions. And multiplying those three things together, we get all three infinitesimals, but once again, we get that r that we saw in the polar coordinate system. So rd theta times dz. And there we have our recipe. So whenever we need to do a triple integral in cylindrical coordinates, that dv in our triple integral, when we translate everything over into cylindrical coordinates, becomes not just dr d theta dz, but r times dr d theta dz. And of course, these can go in any order you want. You just have to take care with setting up the boundaries so that the boundaries come in the correct order corresponding to these things in the iterated integral. We'll do an example in a moment. Here it is. Let's set up an iterated integral for this function of three variables over the region shown below. And I'd better show you the region. Okay, here is the basic shape. These are supposed to be parts of circles right here. And to make things more specific, let's say that this distance here from the z-axis to the inner part of this solid is 3 units, and this distance right here adds on another unit. And let's say this height is 5 units. Okay, that should be enough for us to set up the integral of this function over this region. To begin, we're doing a triple integral of our function over the region R right here. We know what this means. We travel everywhere inside this solid, and at every little spot, we take an infinitesimal bit of volume, we attach a weight to it, the value of this function at that point, that will be different at different places, and add up all of those products. So this is our weighted sum. Now I asked not just for the triple integral, that was no work at all, but for an iterated integral. We could go about doing this in Cartesian coordinates, but it would be very unpleasant. We'd have lots of square roots and things like that. If I want to make life easier, I'm going to do it in cylindrical coordinates, because this sort of region should trigger something in my brain that says, aha, cylindrical coordinates look good here. This is the sort of solid that is more easily described in terms of cylindrical coordinates than Cartesian ones. So let's do that. First, let's look at our integrand. If I'm going to translate all this stuff over into cylindrical coordinates, well, I know what I have to do with dv, that's easy enough, but I have to translate my function over into cylindrical coordinates as well. But that's easy too, because I have my translation equations up here. And of course, you already have them firmly lodged in your head from working with polar coordinates. X squared, since x is r cosine theta, that is going to become r squared cosine squared theta. Similarly, yz, well, we know that y is r sine theta, and z just sits there because z is z in both coordinate systems. So yz becomes r sine theta times z. Now I have to translate my dv over, and the only thing to remember there is to attach that r. We get r, and then I like to do z first, so I'll say dz dr d theta. And now I have to set up my actual boundaries of integration. First, I'm integrating with respect to z. Well, how am I going to do that? The usual way. I imagine a typical point on the interior of that solid. I'm just going to let it vary in the z dimension so that it sweeps out this little elevator shaft, going from down here where z is 0 up to here where z is 5. And that's going to be the same no matter what point I started with. We'll be going from z equals 0 to z equals 5, so my boundaries of integration will be from 0 to 5. Good, now I need to move on to dr. Well, what's happening with r? Once I've got this, I've summed everything up on just that one vertical line segment. Now I want to add up all of the vertical line segments like that as I let r vary. So I want not just that one, but maybe one like this, and one like this, and one like this, and one like this, all the way from here, where r is 3, out to here, where r is 4. So what I'm doing is taking that line segment and sweeping it out in the r dimension so that I get this section of the solid. R is running from here, where r was 3 to r equals 4. So those will be my boundaries on that integral. And then finally, my outermost integral has to do with theta. I've already added up all the elements in my weighted sum on one such slice like this, where theta was fixed. But now I want theta to vary so that this slice fans out and takes this whole solid in. When I'm doing that, I'm just letting theta go from over here, where theta was 0, to somewhere over here, where theta is a little bigger, to over here, where theta is bigger still, to over here, and then finally down here, where theta is pi over 2. So my boundaries of integration will be from 0 to pi over 2. And that's that. That is my iterated integral. I'm not going to bother working this out because that is just a mechanical process and not a very exciting one. There's nothing new involved. The main thing was to see how we go about setting this up. It's the same way as always, just thinking about how we can get to every point in that solid one dimension at a time. I chose to go dz first because I think it's easier on the brain, but in this case it wouldn't have been hard to have done a different dimension first if you had wanted to. Okay, let's do one more in which the boundaries of integration aren't quite so nice. Everything was wonderful here because we just had numbers in our boundary. This was a perfect kind of region for cylindrical coordinates. It doesn't have to be quite so perfect for cylindrical coordinates to be appropriate. So let's see. For our next example, we're going to find the mass of a particular solid, namely the solid given by these two inequalities, x plus y squared is less than or equal to 4, and z is between 0 and y. And we're going to find the mass given this density function, which is a particularly simple one. The density at any point is just its z-coordinate. The first thing we need to do is draw this, of course. So let's start there. I'll put the x and y axes in a slightly unconventional position, because I think that way it'll be a little easier to see what's going on. Let's start with this first inequality. X squared plus y squared is less than or equal to 4. Well, if this were a strict equality, x squared plus y squared is equal to 4, we know that corresponds to a cylinder. X squared plus y squared is equal to 4 in the xy plane is just a circle of radius 2, and since there's no mention of z could be anything, which means it could go up or down as far as we like. But since I already know that z has to be positive, I'm only going to draw it at or above the xy plane. So this is the cylinder. X squared plus y squared is 4. X squared plus y squared is less than or equal to 4 includes the interior of the cylinder as well. Now this cylinder goes up forever, but we do have this other inequality to deal with. We've got this one, and we've got z is greater than or equal to 0. But what about z is less than or equal to y? How is that going to box us in a little more? And it had better, because right now our region is infinite. Well, to understand how to graph this, think about the graph of just z is equal to y. And then once we have that, the inequality should be easy to deal with. Well, z is equal to y. If that was just in the yz plane, that would just be a line through the origin like that. But we're in 3 dimensions. Z equals y doesn't say anything about x, so x could be anything. I could sweep it out as far as I like this way, I could sweep it out as far as I like that way. So you can see that z equals y would be a plane in R3. The solid we're interested in is not just the cylinder. We're interested in the stuff inside the cylinder, and where z is both positive, so above the xy plane, and lower than y. That means we only want stuff that is below this plane. This plane is the set of all points where z is equal to y. It divides all of space into 2 regions. On one side are the places where z is greater than y, and on the other side are places where z is less than y. We want the stuff that's in that latter region and is inside the cylinder. So we have to think about the intersection of this plane and this cylinder. That's not too hard to visualize, because this plane cuts the cylinder clearly right here, and somewhere over here, and so it's going to give us this kind of nice curve, sort of a parabolic shape. In fact, it's actually going to be part of an ellipse. So something like that, which means the solid we're interested in is the stuff that's inside this cylinder and beneath that curve. So the solid we want looks like this blue wedge. Okay, now that we know what it looks like, let's remind ourselves what we're doing here. We want to find the mass of that solid, which we can do because we have a density function for this solid. Its density depends solely on the z-coordinate. So it's denser up here, it's more tightly packed than it is down here. All right, so how are we going to do it? We're going to break this thing up into infinitely many, infinitesimally small pieces. We do that because even though the density varies throughout this solid, if we focus on just an infinitesimally small bit of it, there's not enough room for the density to vary. The density is effectively constant in the infinitesimal neighborhood of any spot, which means I could get the mass of some little bit by taking the density there, that constant density there, multiplying by the volume, that little dV, and then adding all of those things up. And that would give me the total mass of the solid, which means that the mass of the whole solid is going to be the sum, the triple integral, of the density function times dV over my region R. Okay, not so bad. But now, of course, we need to turn this into an iterated integral. And because we took care drawing a reasonably good picture, this shouldn't be so hard. Okay, hopefully that's enough space to put my boundaries. But let's work on the integrand first. Unlike the last example, this one's particularly easy. There's nothing to translate. Normally I'd need to put this into cylindrical coordinates, but it's already in cylindrical coordinates because z is the same in both coordinate systems. As for dv, we know what that is. It's just the product of the infinitesimal bits times r. So I need to remember to put that r in there. And then I will put dz, dr, d theta, because I like doing z first. Okay, that part was easy. Now I just need my boundaries. Well, let's start with z. I want to imagine taking some spot inside my region of integration. And the first thing I want to do is just let it vary in the z dimension. When I do that, what are the boundaries between which it's varying? Well, the lower one is obvious. Obviously, I'm starting down here where z is 0. But what about the upper one? Well, I go until I reach this plane, z equals y. So you might say, aha, I want to put y there. But no, I don't want to put y there because everything over here is supposed to be in terms of cylindrical coordinates. And y is not one of the cylindrical coordinates. Ah, too bad. What can I do? Not a problem. The equation of the plane, z equals y, of course, could itself be rewritten in cylindrical coordinates. The z just stays what it is, and the y becomes r sine theta. Ah, that's better. Now I could say when I go along this line, I'm going from z equals 0 up to here. This point on the plane, z is equal to r sine theta. So r sine theta will be my upper boundary of integration. Now let's move on to the second integral, dr. So far, I have summed everything up just on that one line. Now I want to let r vary and get more lines when r is a little less, right there, or when r is a little more, right there. But keeping theta still fixed. That hasn't changed. And when I do that, I will end up with something like this. Taking this line everywhere where r starts down here and here, close to 0, growing, 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 until I reach the edge of this circle. And that happens, of course, when r is going to be 2. Because that's the radius of the cylinder. So that means my boundaries for the second integral will just be 0 and 2. Good. And now there's only one last thing I have to do, which is to integrate with respect to theta. I've added everything up in this little triangular wedge, but now I have to sweep that around, starting over here where theta was 0, all the way over here where theta is pi. That'll give me, for example, at smaller angles of theta, little triangles like that. And they will grow like that one, and finally they'll get small again over here and disappear again. So as this thing winds around like that, theta is going from 0 to pi, and we will sweep out the entire solid that way. And we now have our iterated integral. And if we compute this thing, we will have the mass we seek. This is a fairly straightforward integral, but again, we have to take a bit more care because at least one of our boundaries is not a constant. So let's do it. For our innermost integral, with respect to z, r is a constant as far as that integral is concerned, so I can pull it through that integral, like that. And to save a little space, let's just think about what's happening. I am now integrating just the function z with respect to z. Well, of course, the antiderivative of that is half z squared. That half will come out through the brackets that we use when we write down antiderivatives. And in fact, that half can come through both of the remaining integrals. So I'm going to go ahead and put a half outside of everything and then just write my antiderivative z squared. When we do that, we end up like this. There's my half and there's my z squared. When I evaluate this, that's going to be r squared sine squared theta minus 0. So just r squared sine squared theta. And once again, to save a little room, I'm just going to put that where this is now. Like that. And immediately these r's combine, so I will get r cubed sine squared theta. Okay, that's much nicer, because now we've just got a twofold iterated integral, and in fact the boundaries we're left with are just constants. So this is a fairly easy one to do. In fact, sine squared theta is a constant as far as this integral with respect to r is concerned, so it can go through that first integral. Okay, now this integral right here, r cubed, well, an antiderivative is of course r to the fourth over 4, so the value of that integral is going to be 2 to the fourth over 4. That's 16 over 4, which is 4. And so I'm going to take that 4, which is the value of that integral, pull it out and combine it with a half to make it 2. And now we're just down to your first class in integration. Hopefully you remember the trick to integrate sine squared. You use a trig identity, sometimes called the half-angle identity, although there are different identities called the half-angle identity. But at any rate, the identity in question is this one. Sine squared of theta is 1 minus cosine of 2 theta over 2. I'm sure you've met that one because that is such a handy identity for integration. Oops, looks like I left off a d theta here. As is its counterpart, the identity for cosine squared, which is 1 plus cosine 2 theta over 2. Anyway, this is what we end up with in this case. And this is easy. Take that factor of a half, yank it through there, it will cancel with the 2. Let's do that up here. So we just end up with this integral, and that's a very easy one. Antiderivative is theta minus something like sine 2 theta, but when we take the derivative of this, we get cosine 2 theta and a 2, which we don't want. So we need a factor of a half to balance it out. Evaluated as theta runs from 0 to pi. And when we evaluate that, we get pi. So that is the mass we were looking for. The mass of that funny-looking solid. Okay, enough of cylindrical coordinates. Let's move on to spherical coordinates. These give us another way of laying down coordinates in R3, so I need to tell you how they work. Given any point in R3, we will define its 3 spherical coordinates as follows. The first spherical coordinate is simply the distance of the point from the origin. There are different conventions for what we should call this first coordinate. I'm going to follow your book in calling it rho. In other treatments, you'll see it sometimes called r, but I like rho better because it reminds us that this is not the same kind of distance we use in polar coordinates or cylindrical coordinates, where we are looking at the distance from the origin to the projection of the point down onto the xy plane. This first coordinate really is the distance from the origin to the point in question. And while I'm on the topic of different conventions for names, you should know, and this is probably one of the most important things you can take away from this discussion of spherical coordinates, that there are a lot of different conventions about spherical coordinates out there. So be sure that you understand what's going on here and don't just try to memorize formulas, because if you see spherical coordinates in another context, somebody else may be using different conventions, and the formulas you've memorized in one context won't work in another. But if you understand what's going on, then it's not hard to make the appropriate adjustments. Anyway, let's move on to the second component of spherical coordinates. Once again, following the convention that your book uses, this second component will be defined as follows. Now we'll project our point down, or possibly up, onto the xy plane, and we'll join that to the origin. This sort of thing looks familiar from cylindrical coordinates. And in fact, the second component I'm going to put here is just our old friend theta, defined exactly as we defined it in cylindrical coordinates. It's this angle right here that we have to rotate the positive x-axis through to reach this line. So that at least is a relief that the second coordinate is completely familiar. But here too, I must warn you that some people use a different convention. In fact, there are 2 different ways people use different conventions here. Some people call this angle phi instead of theta, and still worse, some people make that angle not the second component, but the third component. But for our purposes here, we'll call that angle theta, just like we do in cylindrical coordinates, and it will be the second component, again, just like in cylindrical coordinates. So far, so good. Now we just need to wrap this up with our third component. That is going to be another angle, namely this angle right here, the angle we have to rotate the z-axis down to reach this line right there. And that angle can go by different names, but we are going to call it phi. So our third component is phi. And those are our three components. Now you know how spherical coordinates are defined, but we need to dwell on them and just screw around with them a little bit to get a better feel for them. To begin with, let's just think about the ranges of each one of these coordinates. Rho is straightforward. That's a distance. That could be anything from 0, if we're actually at the origin, all the way out to infinity. We can get as far away from the origin as we like. So no problem there. Second coordinate, well, that's familiar from cylindrical coordinates. That can go anywhere from 0 to 2 pi. And under certain circumstances, we may want to extend that if we want to talk about wrapping around again and again, or going the wrong direction, as it were. But for the most part, we can think of that as being a value between 0 and 2 pi. There's also another way of thinking about theta that's sometimes useful, and this works with cylindrical coordinates as well. Instead of thinking about it as this angle down in the plane, we could think about the plane that's determined by the z-axis and our given point. That would be the plane that this triangle lies in. And to make this clearer, I'm going to draw in one more line in that plane. This one. Now if you concentrate just on this plane right here, that's the positive xz plane, I can think of theta as being the angle between this plane and this one that I've drawn. It's like this is the z-axis is like a hinge between those two planes, and theta is the angle that measures that hinge. It's just another way of thinking about theta that is sometimes useful. All right, what about phi? What's the range of phi going to be like? Like theta, phi could, strictly speaking, be any real number whatsoever, but just as we usually restrict theta to the range 0 to 2 pi, we do something similar with phi, but it's not going to be from 0 to 2 pi. It will only be from 0 to pi. This sometimes catches people off guard, so be sure you understand this. Phi is measuring this angle by which we have dropped the z-axis down. Now there's no particular direction involved. We could drop it down this way, we could drop it down this way, we could drop it down this way. It doesn't matter. Perhaps most importantly, I could drop this back in this opposite direction. In other words, if I rotate it 30 degrees this way, the third coordinate would be 30 degrees, or pi over 6, since we'll measure in radians. If I rotate 30 degrees this way, the third coordinate would be 30 degrees. If I rotate 30 degrees this way, the third coordinate would be 30 degrees. In fact, if we consider this spherical equation, phi equals pi over 6, what would its graph look like? It will be a cone. All the points on this cone have the property that to get there, we have to rotate this thing 30 degrees, one way or another. The distance from the origin could change. We could be up here, or down here, or somewhere up here. The cone, of course, is supposed to be infinite in this direction. And the value of theta could be anywhere from 0 to 2 pi, but for every point on this cone, phi is going to be pi over 6. Similarly, if we were looking at phi is pi over 3, that might look something more like this. It would be another cone, and to get to any point on this cone means that we've rotated through 60 degrees, pi over 3 radians to get there. What would the graph of phi equals pi over 2 look like? That wouldn't be a cone at all. That would be the xy plane, because every point on this plane is going to have some certain theta value and some certain rho value, but its phi value will definitely be pi over 2. And we could continue on down the other way. If we looked at, for example, phi equals 5 pi over 6, that would be all the points we could get to by rotating through 5 pi over 6, 150 degrees, in any direction. Theta could be anything, rho could be anything. I hope you see that the graph would look like this. And as we let this value approach pi, that angle would be getting closer and closer to pi, so our cone would be getting tighter and tighter and tighter. And at phi equals pi, we would just have the negative z-axis. Anyway, this is why I say that the natural range of phi is from 0 to pi. If you allow rho and theta to roam through their usual ranges, and then just let phi go from 0 to pi, you get the entirety of R3. Anyway, you can see from this little game that one set of shapes that is easily described with spherical coordinates are cones, and another set of figures that are easily described are, not surprisingly, spheres. For example, the graph of rho equals 1 is just the sphere with radius 1, because a point is on this sphere if and only if it's 1 unit from the origin. But that's just saying that its first spherical coordinate is 1. Similarly, if we were to look at rho equals 2, that would be this sphere centered at the origin with radius 2. And you get the idea. Rho equal any positive constant would give us a sphere centered at the origin where the constant is the radius of the sphere. So spherical coordinates are wonderful for spheres, and they're quite nice for cones too. Now you know what they are, we need to talk about the translation equations between spherical and Cartesian coordinates, and of course, we need to talk about how to do integration in spherical coordinates, which will come down to finding a formula for dv in spherical coordinates. First things first though, let's do the translation equations. These are fairly straightforward, at least if you are comfortable with basic trigonometry, which you should be by this point in your mathematical career. Still, the derivations take a little work, and it's very important that you understand it, because as I've said, there are so many different conventions for spherical coordinates that if you're reading a paper or a book where somebody else uses different conventions, you are probably going to have to scratch out the translation equations on your own. If you can follow what I'm about to do, you'll have no problem doing that. We want to be able to move back and forth between rho, theta, and phi, our spherical coordinates, and x, y, and z, the Cartesian coordinates of our given point. We just need to do a little trigonometry. We have a couple of right triangles here, this one which lies in the xy plane, and this one which is perpendicular to the xy plane. And we might even use this one up here too. In fact, what we're about to do would be a great exercise for a trigonometry class. Let's get started by finding x, y, and z in terms of the spherical coordinates, rho, theta, and phi. This is just going to involve bouncing around a lot between these various right triangles we're working with here. Start with x. X and y will be easy to find once we know the hypotenuse of this triangle in the xy plane, because we already know this angle theta. X is going to be the hypotenuse times the cosine of theta, and y will be the hypotenuse times the sine of theta. So all we really have to do to get x and y is come up with that length right there. And that's not hard. That length right there is the leg of this triangle. And we already know the hypotenuse of this triangle, rho, and I even know one of the angles as well. Well, of course I know this right angle, but I know one of the acute angles as well. Since this angle right here is phi, just by basic properties of parallel lines, I know that this angle right here must also be phi. And now I have enough information to determine this triangle, which not only will give me that, but it will give me z as well. So in effect, I'm done. Now let's just carry out the details. The leg of this upright triangle is, thanks to SOHCAHTOA, rho times sine of phi, because the hypotenuse is rho and it's opposite the angle phi. But then that tells us what x is. It's the hypotenuse of that triangle times the cosine of theta. So x is rho sine phi cosine theta. Similarly, y is going to be rho sine phi sine of theta, because y is the hypotenuse of this triangle times the sine of theta. And finally, z is the hypotenuse of this triangle times the cosine of phi. So z is rho cosine phi. Good, so we've got our spherical to Cartesian conversions. Now we want to go the other way around. We'll start with rho. Well, this is a job for the Pythagorean theorem. Rho is the hypotenuse of this triangle, so rho squared is z squared plus the square of this side, but that side in terms of x and y is the square root of x squared plus y squared by the Pythagorean theorem on that right triangle. So now applying Pythagoras to this triangle, I get that rho squared is the square of this, which is x squared plus y squared, plus the square of that, which is z squared. So there it is. Rho squared is x squared plus y squared plus z squared. Next, we want to get theta in terms of the Cartesian coordinates. Well, that's easy. It's the usual recipe for theta. Just looking at this right triangle down in the xy plane, as always, we see that the tangent of theta is y over x. So some things never change, at least if you adopt this convention for naming that coordinate, which is one of the reasons why I prefer it that way. And now we need to get phi in terms of the Cartesian coordinates. Well, we can get that off of this triangle right here. There's actually several ways we could do it. One would be to note that the tangent of phi would be this side over this side, so tangent of phi is root x squared plus y squared over z, and that would work, though I prefer to think about the cosine of phi. We could say that the cosine of phi is the adjacent leg, z, over the hypotenuse, rho, but as we start to write that down, we realize, wait a second, I can't put rho here. The whole point is to get phi in terms of Cartesian coordinates. But I already know what rho is in Cartesian coordinates. It's just going to be the square root of that stuff. So I can write it that way. It's not really a big deal whether you write it this way or say that tangent of phi is this stuff over z. I tend to like cosines just because the inverse cosine has a range from 0 to pi, and that's exactly what the range we talked about before of phi should be, whereas the inverse tangent goes between minus pi over 2 and pi over 2, which works, but I like to keep everything positive. As long as you can draw this picture and think your way through the basic trigonometry, you can scratch these out whenever you need them. And that is good because you don't want to memorize them. Please don't. Please do make sure that you can derive them when you need them. Everybody should know the basic polar coordinate translation equations off the top of their head. If somebody wakes you up in the night, you should be able to say x is r cosine theta. There's no reason why you should say y is rho sine phi sine theta. Spherical coordinates just aren't used as frequently as polar coordinates is one reason. Another is that this is just a mess. And a third is that your next door neighbor probably uses different conventions for spherical coordinates. The fact that you've memorized this doesn't mean anything. You need to figure out what your neighbor's conventions are, and then draw a little picture and come up with the translations yourself. Anyway, there we have them. Not so bad and a good workout for your basic trigonometry. Well, you know what comes next. We have to figure out the volume element in spherical coordinates. We have to think about what dv is going to look like in terms of d rho, d theta, and d phi. The picture that justifies the formula for dv in spherical coordinates is not an easy one to draw. I'll do my best, but the basic idea should be familiar. We start with a point in R3. That point has some spherical coordinates, rho, theta, and phi, and we're going to increase each of those spherical coordinates by an infinitesimal amount. That will generate some little box, and once we know the dimensions of that box, we can multiply them to get the volume dv. It will help to go ahead and draw rho, theta, and phi in the picture because we will need them in what follows. There's rho, there's theta, and there's phi. When we make a little infinitesimal change in rho, that will move us a little bit in this direction. That one's easy to see. And when we make an infinitesimal change in phi, that will swing this down a little bit. That's fairly easy to see as well. It's theta that is probably the trickiest one to see here. So I'm going to start with that one before the figure gets too cluttered up. Adding this line should help us see what's going on with theta. And remember, as we discussed before, we could think of theta as the angle between this plane right here and this plane that contains the positive z and the positive x-axes. So increasing theta by an infinitesimal amount, d theta, is simply going to take this plane in the back and swing it around by a little bit more. So we can think about d theta right here. Or we could think about it down here, but I'm going to not draw that in because it will get very messy very quickly. At any rate, when we increase theta by this little bit d theta, our point is going to rotate slightly around the z-axis. So that will be one edge of the little infinitesimal box that we are generating. Well, we know from our previous work that the length of that little arc is going to be the product of this angle, d theta, and this radius, whatever that is. That length is going to be rho sine phi by basic trigonometry, because rho is the hypotenuse, and we're looking at the leg opposite phi. That means that this length right here, that arc, will be rho sine phi d theta. Good. The hardest part is done. The rest is pretty smooth sailing. Let's consider an infinitesimal increment to phi next. From my starting point here, if I were to increase phi an infinitesimal amount, that would take this point and rotate it down inside this plane right here. It would rotate it in that plane just an infinitesimal amount around the origin. And it would trace out an arc like this. What's the measurement of that arc? Well, this angle right here is d phi, this little infinitesimal change to phi, and this is a slice of pi, where the radius of the whole pi is rho. That means that this arc length will be the product of those two quantities. In other words, it will be rho d phi. Good. That gives us two adjacent edges on our little box. To get the third, all we have to do now is increase rho by an infinitesimal amount. And that's very easy to see. When we do it, the result will look like this. And those three adjacent edges generate a box that looks like this. This edge, of course, is d rho, and now I can write down an expression for the volume of that infinitesimal box. dv will be the product of these three dimensions, namely rho squared sine phi d rho d theta d phi. And we've got it. With this formula in hand, we can now take a triple integral that's defined over an appropriate region and convert it into an iterated integral involving spherical coordinates. Let's do an example. As you know, the volume of a sphere with radius r is 4/3 pi r cubed, and you've almost certainly seen a proof of that by taking a semicircle and revolving it around the axis and using some basic one-variable calculus to come up with the volume. You may have seen other proofs as well. Let's do it with a triple integral and spherical coordinates. We know that the volume of the sphere can be found by breaking the sphere up into lots of infinitesimal pieces and summing up their volumes. In other words, taking all those little dv's and integrating over the entire sphere. Now, this triple integral could be rewritten as an iterated integral in various ways. We're going to do it with spherical coordinates. So our integral will become something else. dv, we know, is going to be translated like this. And now we're just going to need to write down our iterated integrals and determine the boundaries on each one. To do that, as always, we'll think of a typical point within our region of integration, such as this. And since we will first be integrating with respect to rho, the idea is that we're just going to let rho vary so that we will be sweeping out like that. And as we move along that line, we are letting rho run from 0 out to r, which is the radius of our sphere. Good. And remember, r is a constant in this particular problem. This is not a coordinate as it might be with polar or cylindrical coordinates. All right, now we're moving on to theta. When we integrate with respect to theta, geometrically what's happening is we're taking that radius and only letting theta vary. When we do that, we sweep out a cone by letting theta vary from 0 all the way around to 2 pi. So the boundaries on our next integral will be 0 to 2 pi. And finally, we have to integrate with respect to phi, which is like taking this cone, which has some fixed angle of phi there, and letting phi vary from 0, where we have just a straight line, to something small, which gets us a cone like that, to something bigger, which gets us a cone like that, to something bigger still, which gets us a cone like that, all the way down as phi varies from 0 to pi, so that our boundaries of integration on our outside integral will be 0 to pi. Good, now all the hard work is done. We have turned our triple integral into an iterated integral, and this is a particularly easy one. Think about this innermost integral. Sine of phi is constant with respect to that integral, so it's just going to sit there. And the integral of rho squared with respect to rho, as we run from 0 to r, is clearly going to be r cubed over 3. I'm going to go ahead and pull that third out through the integrals and just leave the result, the r cubed sine phi. That will give us this expression. Oh, actually, it's nicer than I thought. I forgot my own warning for a second. R, remember, is a constant. That's just the radius of the sphere. So I can go ahead and pull this r cubed through the integral as well. All right, now when we look at this inner integral, we have sine phi, which we're integrating with respect to theta. Well, as far as theta is concerned, sine phi is a constant. And when you integrate a constant over an interval, you just multiply that constant by the length of the interval. So that is all going to become 2 pi sine phi. And I'll go ahead and pull the 2 pi through the integral as well, leaving us with this expression. And you may or may not know off the top of your head the unexpected result that when you integrate the sine function between 0 and pi, which gives you the area under one arch of the sine function, the result is exactly 2, which I always find surprising because you somehow expect it to involve pi, but it doesn't. It's just an integer. And if you didn't know that off the top of your head, no harm done. You just integrate this in the usual way. Either way, this is all going to be equal to 2, which means this gets multiplied by 2, which gives us 4/3 pi r cubed, exactly as we claimed. So there it is, the famous result. And with that, I will bring this long lecture to an end. Kwaherini.